Alrighty. Let's see if everything's set. Okay. Alright, so yesterday was the medium version of this, and now it's the hard, huh? Maybe my streak ends at around 1. Alright, there is an undirected tree with n nodes labeled from 1 to n. We're at node 1. The tree is represented by 2D interior array edges of n minus 1 length, where edges I is uv indicates an edge between nodes u and v. Okay, yep. Initially, all edges have a weight of 0. You must assign each edge a weight of 1 or 2, same as yesterday. The cost of the path between any two nodes, u and v, is the total weight of all edges in the path. Yep. You're given a 2D integer array of queries. For each query at I, which has u, v, determine the number of ways to assign weights to edges in the path such that the cost of the path between them is odd. Return an array answer where answer I is the number of valid assignments for queries at I. Since the answer may be large, apply modulo 10 to the 7th, 10 to the 9th plus 7. For each query, disregard all edges not in the path between node u and v. Okay. Right. So this is really gonna use yesterday's deal. But I think that I might have an idea as to what's going on. So queries 1 to 1, there's 0 ways to make that odd. 1 to 2, there's 1 way to make that odd. You label this edge 1. Query 1 to 4, it's either going to be 1, 2 or 2, 1 as the edge weights here, so it's going to be 2 ways. 3 to 4, there's 1 edge between them, so it's 1 way. And then 2 to 5, there's the path length is 3, 1, 2, 3. So either one of them is odd, in which case there's 3. So if there's 3 edges and the sum has to be odd, then it has to be like 1 odd and 2 evens, or all 3 of them odd. If all 3 of them odd, there's 1 way of doing that. If one of them is odd, then there's 3 ways of doing that. And that's a total of 4. Okay. So the general thing is from yesterday's problem. In general, the number of ways to assign weights such that the total is odd is equal to where the path between nodes is, let's say, p, the length of the path. Is p is equal to like p choose 1 plus p choose 3 plus p choose I should use capital p choose 3 plus p choose 5 plus p choose k, where k is odd, which equals 2 to the power of 2 to the power of p, or p minus 2 to the power of p divided by 2, which is equal to 2 to the power of p minus 1. So in general, it's because the sum of the odd choices is equal to the sum of the even choices. They add up. And if you know the Pascal's triangle or the binomial expansion for a plus b to the power of n, the number of ways to doing that is like 2 to the power of n. And since half of them are choosing odd versus half of them are choosing evens, then the ways of choosing odd is 2 to the power of n divided by 2. And 2 to the power of n divided by 2 is just 2 to the power of n minus 1, right? So this exponential properties. So here just need to find the kind of path length for each query, and then that should basically solve it. Because calculating this for each thing after that should be pretty straightforward. So to calculate the path length between queries, I guess I should probably make a graph, and then I have to have some way of identifying. This is pretty standard problem, identifying like the closest parent for every pair of nodes. Closest parent. Let me think, how would I do that? So is it recursion? Now it is. So I need to quickly identify the closest or the earliest parent, earliest common parent as you go upwards for each query. Because like it's just like however long it takes to get to that parent from one node plus however long it takes to get to that parent for the other node, the sum of those two things should be the length of the shortest path. We need to find the shortest path length between the nodes of the query for each query. How would I do that? I could make for each node, how many nodes are there? It is kind of a tree, right? 2 to the nth, or 10 to the nth, 10 to the fifth. I mean, technically it could be a very long tree, long single branch tree. I was thinking maybe just for each node storing a list or array of parents at each level to that, but that could be too long to do the comparison. Like if one node has like 10 to the 4th parents, it's just an extremely long single branch. Yeah, this should be a simple problem. I wish I had better memory. So if I recursively go upwards, so if I store for each node the level that they're at, and then keep on going upwards, that might be too long, to be honest. Kind of want to do this in constant time. If I traverse upwards, then it technically is, in the worst case, maybe like, if it's a single branch, it's O of n, and that would make this O of n squared if I have to do it for n queries. So the hard problem just boils down to whether or not I can find the path to the nearest common ancestor. the length of the path. Length of the path to the nearest common ancestor. For each node. For each node, what? There probably should be like log n is the time complexity of this. It can't be n. That's just too slow. So like if I said that 2 and 5, how would I do like log n to find that 1 is the common ancestor, the earliest common ancestor? Can I do a search? Can I guess? Then that would need, that kind of requires storage. I kind of don't want to have storage here either. I want to have storage of the path. That'd just take too long. That'd be like n squared as well. Two and 5. Common ancestor of 2 and 5 is 1. 3. The binary. I don't think this needs to be a binary tree. Tree is represented with this thing. Yeah, it's just, it doesn't need to be binary. So 1 has 2 and 3. 3 has 4 and 5. One has 2 and 3. Can I store some sort of hashable marker as to which area of the tree this is? I think when I've done like closest common ancestors, generally been for binary trees. Even if I don't even remember how to do it, I feel like the fact that this is not a binary tree is making this extra complicating. So 1, 2, 3, 3, 4, 5. 3, 4, 5. So 5 goes up to 3. 3 goes up to 1. But if it's an extremely long branch, then it could be 5, go up to 4, go up to 3, go up to 2, go up to 1. And that would just take forever and a day. 2 goes to 1. 1 goes... Yeah, it's just not going to work, is it? 2 goes to 1, 1 goes to 3, 3 goes to 5. Like, obviously you can do some sort of search from one node to get to the next node, but 5 goes in a stack, then each time it crosses the node in the stack, it goes to its neighbors. From its neighbors goes to its neighbors. From its neighbors goes to its neighbors. So that pretty much searches the whole tree for this. Only I could somehow organize the branches in the tree to, like, say that 5 is in a particular branch that includes 3. 3 is in this particular branch, or 4 and 5. 4 and 5 map to 3. 3 map to 4 and 5 map to 3. Yeah, it's just too slow. It's like, I'm thinking of O of n ways of doing this, like O of n ways to solve for the shortest path. It needs to be O of n log n, or it needs to be O of n, O of log n, not O of n. I mean, preferably it'd be O of 1, but I don't think we can store that much information. Or maybe 1 to 2, 1 to 3, 1 to 2 and 3. 3 goes to 4 and 5. Man, this cannot be this bad. 68% pass rate, that's pretty good. Pretty good, pretty good. Path from 3 to 4. 4 goes up to 3. Bingo, bango, bomb. I mean, it's just not sorted is the thing. Yeah, when I like find common ancestors, generally maybe sorted as well, instead of just having an unsorted thing. 1, 2, 1, 3. To know that 4 and 5 are underneath the 3 and not. So like if this 4 was underneath the 2, then it'd be 4, 2, 1, 5, 3, 1. Four, 2, 1, 5, 3, 1. Oh, 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 oh. Can't believe this is gonna stump me. 4. There just has to be a way. Has to be. 4 goes up to 3, 5 goes up to 3, 2 goes up to 1, 5 goes up to 3. One includes 3 and 5. Yeah, if like for each node I store all the children of that node, that would take n squared things as well. For each node store all the children and like grandchildren and all the descendants, I guess. For each node, if I store all the descendants of that node, would that even be fast? It might take up too much memory and also not be fast enough. It'd be fast in the verification, not in the guess. 1, 2, 1, 3, 3, 5. Constraints, edges, it's not circular, or it's not, there's no cycles. One, 3, 5, 1, 2. One, 3, 5, 1, 2. 2 goes up to 1, 5 goes up to 3. I guess 5 goes up to 3 first, since we can store the depth of each node. 5 goes up to 3, and then 2, 3 goes up to 1. I mean, you can do a side-by-side comparison of depths. So you always only go up the node that has a lower depth. So then you just, once you have the nodes be the same depth of comparison, then you just go up their parents until you find one that's the same. But then that still seems like an O of n process, especially if you have like, I don't know, just two single branch kind of roots. Like if 2 was on like a 1,000 long link chain at the end of that, and 5 is also on the 1,000 long link chain separately, it'd be like basically 2,000 steps to reach the one that's common. It's just too slow. That's just too slow. If I could somehow store the chain link, if I can somehow store the chain link, then I could jump to a certain depth on the chain link. I could jump to a certain depth on the chain link. And then do what? I could store a certain depth on the chain link. Huh. So if I could do like, let's say it is And then, so let's say 2 is on something that's extremely long, that's single chain. And 5 is on a single long chain separately from that. How to do like a log n search for the common SSO. Feels like I need to find an O of log n method of finding common ancestor. Finding earliest common ancestor. Two, one, how would I store that linked list? 1 to something to something to something to something. How would I jump to an earlier one? Jump to one that, how would I jump to it? I wonder. Like the nodes themselves don't have unique values, do they? No, they do have unique values because the nodes themselves have to be uniquely identifying for the edges to work. The nodes have to be uniquely identifying. So if I have something that's like 1 and then 3 and then all odds up to 5, or all odds in this chain to 5, and let's say this other chain is all evens, then can I use a hashing? Can I hash 1, 1, 3, can I somehow use some hashing mathematics? Can I use some sort of hashing mathematics? Would I my hashing mathematics is pretty bad. Like if the chain itself is like, let's say 1, 1, 4, 6, 10, 2, and the other chain is 1, 3, 5, 7, 9, 5. Is there a mathematical way to store the information about the chain itself? Store the information about the chain itself. Like, what if I, ooh boy, 1, 4, 6, 10, 2. Like, is there like an XOR operation I can do somehow? Like if I somehow store some sort of XOR value that is 1 XOR 4 XOR 6 XOR 10 XOR 2, like the XOR of all the nodes in the path from the start to this node, 1 XOR 3 XOR 7 XOR 9 XOR 5. What happens then? What happens when I XOR those two paths? Can I somehow retrieve 1 XOR whatever? I don't think so, actually. I'd retrieve 1 XOR those values at best, but then I have to know the length or the number of values that are being XOR'd. Alternatively, if I somehow did have this thing 1, 4, 6, 10, 2, if I somehow had that stored as an array, I could jump to certain elements within it. Like I jump to index 0, find that it works, or maybe jump to index 2, find that it's different, so therefore jump to index 1, find it's different, jump to index 0. Binary search that way. That would be log n. Then I would need to have this stored information about 1, 1, 4, 6, 1, 4, 6, 10, 2, 1, 4, 6, 10, 2. One goes to 4, 4 goes to 6, 6 goes to 10, 10 goes to 2. Can somehow 2 jump all the way to 6? How would I know that 2 has an ancestor of 6? 2 has an ancestor of 6. 1 hash to, I do a hash of 1, giving me 4. One hash with 1 hash width, one, 4, 6, 10, 2. It wouldn't be that hard to. No, that'd be a really long tuple. That would be a really long tuple. One, 4, 1, 4, 1, 3. So we need 2 separate arrays for that. 1 to 4, 1 to 3. That sounds like a linked list. This really shouldn't be this hard, is it? Find the earliest common ancestor. I must have done practice problems with something similar, but maybe they just used something with more structure than a graph like this. Probably a binary tree. Finding the earliest common ancestor. 2 goes to 10, 10 goes to 6, 6 goes to 4, 4 goes to 1. If I make a tuple, if I hash 1, 4, 6, 10, if I do 1, 4, if I make a hash 1, 4, 6, 10, what if I hashed? What if I made a hash of 1, 4, 4, 6, 6, 10? 1, 4, 4, 6, 6, 10, 10, 2. And let's say 1, 4 hashes to A. Does that solve it? And then 4, 6 hashes to B. 6, 10 hashes to C. 10, 2 hashes to D. I would still need to. I don't think that solves anything. 1, 4 hashes to A. A 6 hashes to B, B 10 hashes to C, and then this is C2. I mean, I guess that what does that mean? One 10, 1 4. So if I do 1 3, 3 7, 7 9, 9 5, 1 3 hashes to B, 3 7 hashes to C. Still needs to have some way of, for each node, some sort of upwards pathing. For each node, some sort of upward pathing. Oh, all right. I think it's time to call it another stumper. Wow. All right, I'll try to think about it while I'm sleeping. Maybe I'll come up with a dream of a